Look at a raw spreadsheet. Thousands of rows of data are completely useless to human eyes until we organize them. To actually make sense of raw information, we need to answer two basic questions. Where is the center of this data, and how far does it spread out from that center? Let's start with a simple number line to find our center. Imagine we have a data set of just 5 test scores, 70, 2 80s, a 90, and a 100. We immediately spot the most frequent score, the mode. That's 80, since it appears twice. If we line all the scores up in order of magnitude, we can also find the physical middle of the group. That's our median, which also happens to be 80 in this set. Then there is the arithmetic mean. If we add all 5 scores together and divide by 5, we get 84. You can think of the mean as the exact mathematical balancing point for the visual weight of the entire dataset. The mean is the most common standard for measuring central tendency because it includes every single value in its calculation, but it has a strict mathematical weakness. If one student scored a 10, that extreme outlier drags the mean down, throwing off the balance. In asymmetrical distributions, the median gives you a much safer, accurate picture of the typical score. 5 isolated test scores are easy to manage, but what happens when you have a massive table of hundreds of data points organized into ranges instead of exact numbers? You can't run a calculation on a range. Look at this frequency table showing monthly sales. To work with grouped data, we find the exact midpoint of each class interval. A range like 300 to 350 converts into the usable integer 325. Now we can calculate our mean. But finding the center is only half the job. Look at these 2 dot plots representing the ages of patients in 2 different hospital wards. Both wards have a mean age of 40. But one ward is completely filled with 40-year-olds, while the other is a mix of infants and 80-year-olds. The center is identical, but the spread is completely different. To measure this spread, the quickest tool we have is the range. We simply subtract the absolute lowest score from the absolute highest score to find the total mathematical distance covered by our data. The flaw here is that the range only evaluates the 2 extreme edge cases. It tells us absolutely nothing about how the rest of the data behaves inside those brackets. To measure the internal variability of the dataset, we need a sharper, more rigorous tool. This calculation table will help us determine the standard deviation. This is the definitive measure of dispersion because it calculates the average distance of every single score from the mean. We start by taking the midpoint of a class interval and subtracting our overall mean. Because the specific value falls below the mean, it results in a negative deviation. We can't have negative distances mathematically canceling out positive distances later on, so we square that deviation to make it positive. Then, we multiply that squared number by the frequency, which accounts for every data point grouped in this specific interval. Let's apply this. Take a look at the 3rd row. Pause the video, calculate the squared deviation, and then multiply it by the frequency. Hit play when you are ready to check your answer. If you got these numbers, you understand the logic. To finish, we add that final column to get the sum of all squared deviations, divide by our total number of items, and finally take the square root. That gives us our exact standard deviation. Standard deviation is the most reliable tool in statistics because it refuses to ignore any data. It uses every single data point to prove exactly how much the numbers fluctuate from the norm. Now, suppose you are analyzing 2 stocks, and both show a standard deviation of $2. But one stock costs $10 a share, and the other costs $500. A $2 swing carries a very different level of risk depending on that baseline price. To accurately compare datasets with completely different scales, we use the coefficient of variation. We divide the standard deviation by the mean and multiply by 100 to convert the risk into a clean percentage. Run the formula, and the context becomes clear. The $10 stock has a 20% variation. It is highly volatile. Meanwhile, that exact same $2 swing on the $500 stock represents a microscopic 0.4% variation. Here is your complete map for evaluating any dataset. On the left, we determine the center using the mean, median, and mode. On the right, we evaluate the spread using the range, standard deviation, and coefficient of variation. Go ahead and save this frame. Raw data is a mess of isolated numbers, but these tools give them structure. Measures of central tendency give you the typical story of your data, while measures of dispersion prove exactly how reliable that story actually is.